you're going to notice that our slow step is step 2, right? Now, if you look at the slow step, we might, again, be tempted to just be like, hey, the rate is dependent on the slow step. So it's going to be dependent on the concentration of NOBr2. Now, what's the problem with this rate law here? Yeah, NOBr2 is an intermediate, right? It is produced in the first step, used in the second step, but we don't have it in the overall reaction. So this rate law is stinky poo-poo. We can't use this because this is an intermediate, okay? All right, so we need to do all that fancy schmancy math in order to write the rate law, the integrated rate law here. So I'm going to go through how to do this because this may or may not be on your tests. Who knows?
It's gonna be on.
You know, what if I just say that and then don't put it on the test just to make you study it? That would be. See, you never know what's going on in my mind, though. You guys don't know what's going on in my dark, twisted mind, okay? I have, yeah, anyway. All right, so let's go through the steps. So first thing we want to recognize, and this is a principle we should know, is that the forward rate is going to be equal to the reverse rate, okay? And this is the case for all reactions. The forward rate is going to be equal to the reverse rate. Now, what we're going to do is we are going to basically just expand these two, I guess we'll call them variables, right? And then we're going to expand on these. So the forward rate of reaction 1, right? Because the reaction 1 going into step 2 is going to equal K for the forward rate of 1. And then the concentration of NO and Br2. Okay. So basically, we're just writing the rate law for step 1 right here. Okay. And then it's K1 because it's the K value, the rate constant for the first step. Okay. All right, guys, we're going home. Everyone pack up. Okay. That would be great. All right, anyway. But now we're going to take a look at the reverse rate. Now, if you guys take a look at the reverse rate of this reaction, it's going from step 2 back to step 1, right? So it's going to be the K reverse of 2, and it's going to be dependent on the concentration of NOBr2. Okay. So basically, we're just talking about this side on the left is talking about the rate going this way from left to right for step 1. And then K reverse is the reverse rate, so going backwards in this reaction. Okay, that's what it's talking about. I know. Okay, does that make sense though, guys? Okay, so now what we have to do is we need to just rearrange these variables in order to figure out what the integrated rate law is. Okay, so first thing that we want to do is, if you guys take a look at the problem with this rate law is that it's dependent on the concentration of the intermediate, right? But we don't know the concentration of the intermediate, so we have to mathematically calculate it. So what we're going to do is, you guys should notice that this is the same variable as this, and so we're just going to isolate this variable and then plug it in for this value right here. Okay, it's just a basic substitution algebra thing. Okay, so we're going to divide both sides by K reverse. And so on the right side, we're going to have the concentration of our intermediate. And it's going to be equal to K1, concentration of NO, Br2. Basically, the entire left side divided by K reverse. Okay. Alrighty, so far so good? Okay, so we're just going to take this value right here and substitute it into this rate law for the concentration of the intermediate. So we're just going to write it in. So we're going to write that the rate is equal to K, and this is going to be K2, right? Because it's for step 2. And then it's going to be, we're going to multiply it with K1. And I'm going to do it like this, just so it's a little easier to look at. But something like that. Alrighty. And that's it. That's going to be the integrated rate law. That's it.
On the test, would you give us like numbers for like the values?
Yeah, you might get numbers, but other times they'll just ask you to write the rate law, and this is what you'll write. Just like how normally we write K, you're not always going to know what the rate constant is. And so similarly, this value right here would be your K, and that's going to represent the rate for step 2, 1, and then the reverse reaction. Yeah. Yeah, if you can memorize this, then that's fine too. Yeah. But this is your proof. If they say show work, then yeah, you would have to add all that. Okay. Any other questions? Okay, guys, congratulations. That is unit 10. That is kinetics. We are all done with that unit. Woohoo! Okay, so we are gonna do some practice problems. And so I'm gonna put them up here. So I have not posted on them on Canvas. Do you guys want them on Canvas?
Yes.
Okay.
I can't read them.
Okay, that's fine. Give me 1 second then. Okay, guys, let's go over this problem. So a lot of information at the top. Hopefully you got to read that information. But let's go over this. Okay, so we got our reaction. Ozone oxidizes HSO3 minus. We got the reaction right there. But yeah, let's go to part A. So the data above shows us the rate law, or expresses the rate law, and this is the rate law right there. Okay, so based on the data above, explain why the data is consistent with O3 being a first order reactant. Now, the first thing we want to do is figure out what in the world is a first order reactant, right? So if you guys remember, first order basically just means that the rate does not change with the concentration. If you guys remember, second order, it's one where if you change the concentration, the rate increases, right? The rate at which the reaction takes place increases. First order is the rate basically stays constant. Okay, so another way of writing that would be rate stays constant with regardless of concentration. Okay, that's what a first order reactant is. Okay, so it doesn't matter if you have 1 molarity of the reactant, doesn't matter if you have 2 molarity, 3 molarity, 4 molarity, right? The rate is going to stay constant in proportion to the concentration. Okay, so if you double the concentration, the rate also doubles. If you have the concentration, the rate is also going to have. Okay,
So it's consistent.
yeah, maybe does not change this the wrong way. That's right, changes in proportion. Sorry, maybe that's a better way to write it. Okay, first order is where it changes in proportion with the concentration. Okay, now it changes to that. Sorry, is that more clear? Yeah. So example, you 2x the concentration, that's going to equal 2x the rate, etc., etc. So that's what a first order reactance is. And so now based on that, with that information, we can go into the graph and see if the data is consistent with that. Okay. Okay, now the easiest way to do that is to just look at the half-life. Okay. So let's I'm gonna zoom in on this graph. Okay. So half-life is an easy way for us to compare how the rate changes over time in proportion to the concentration, okay? So if we take a look at this graph, let's first look at the first half-life, okay? So anyone want to take a shot at it? What's the half-life, the first half-life? Yeah, Robbie.
0.01.
Yeah, 0.01 seconds, okay? So the first half-life is going to be 0.01 seconds, okay? Because that's the rate at which, or that's the time it takes for the concentration to drop in half. That's the rate, basically, okay? That makes sense, guys? Okay, now let's take a look at the second half-life. So the first half-life ends at 5.0 times 10 to the negative 6 molarity. What about the second half? At what time period does that concentration drop in half? Yeah, 0.02, right? Because it's going to be 2.5, right? 2.5 times 10 to the negative 6. So let's compare the time it takes between the two. So the first half-life takes 0.01 seconds. What about the second half-life? What's the time it takes to go to the second one? Yeah, also 0.01. So if you guys notice, between here and here, the concentration changed, right? And between here and here, the concentration changed again. Did the rate change? No. So that's how we can know this is a first order reactant. Okay, we can say that the way that we would explain it is that O3 is a first order reactant. So O3 is a first order reactant because the half-life time is constant. Okay. And what that tells us is that as you change the concentration, the rate at which it's gonna react is going to be in proportion to that concentration. Okay. And then so you can basically just explain to me what you did. You can say you would just use some data from the graph. You can say the half-life is 0.01 seconds. The second one is also 0.01 seconds. And so it's going to stay constant. Yes.
I said exponentially decreasing.
Yeah, you want to be, yeah, that's another way to, you do want to be a little bit more specific than that, because are you talking about exponentially decreasing in the sense of like to 1/2, power of 1/3, 1/4. So if you want, just be a little bit more specific. And so that's why referencing the numbers would be a little bit helpful. But yeah, that is correct. Okay. Any other questions on A? You guys have a lot less energy than 10 minutes ago. This is great.
What happened 10 minutes ago?
They were happy.
It's
And then-
just you up there.
Can you teach me that power? How can I walk into a room and just depress everybody?
It's take years. to
Take
practice.
years. Oh my gosh. I don't know if I have years left. Goodness gracious.
The-
All right.
All the chemicals.
Yeah, all the chemicals. I'm gonna die soon. We get some weird disease. Grow a third head. Okay. Let's go to B. B is pretty easy. We already did that, right? What's the half-life? Yeah, 0.01 seconds. Okay, so if you guys take a look at your equation sheet, there's a half-life formula on there, right? Yes. Let's all find it. So take out your equation sheet, see if you can find the half-life formula on there. Yes. They're up here. If you guys need one, you can come up here. I will give them out. You guys lost my gift to you?
Yeah.
I said it was my folder. Better to say gift or something? I mean, I'll give you one back. How many you got?
Well, I like the joy.
Oh, thank you. Okay, so if you take a look at the equation sheet and go to somewhere.
It's back.
No, not in the back, the front. Huh? Okay, you guys should see in the front, literally the very bottom, in the section that says kinetics, you guys will see the half-life formula, right? It's equal to 0.063 divided by K. You guys see that?
Yes.
Yeah, it might be somewhere different. If it says natural log 2, that works too. All right, let's see what the other one said.
Yeah. Yeah, 1.73.
That's probably the older one. That's me.
It's in the bottom.
Yeah, the newer one has it on the bottom. The older one has.
It says-
Wait, what did you?
No, but that's a lot of difference.
Yeah, that's on that.
You know,
I just wrote it. Did I say 693?
Yeah.
Dude, I'm out of my mind. Sorry, guys. Sorry. English, my second language. I can't read this. 693. Sorry. Natural log of 2. Okay. I'm sorry. Rewind. Okay, so if you take a look at the bottom of the paper, it says the half-life is equal to 0.693 divided by K. Did I write it correctly this time? Yes. Okay. So, based on the information that we have, do you guys think you could solve for K? Yes. Okay, it's just isolating the variable. We have the half-life. So I will give you guys about 2 minutes. See if you guys can calculate for the rate constant. Okay. If you can give me the units of measurement, that'd be incredible too. Answers? All right, so we can basically just solve for the missing variable, right? We're solving for K here. So if you want to plug into your calculator, it'd be K is equal to 0.693 divided by the half-life, which is 0.01 seconds, so 0.01 seconds. And if you calculate that, you should get about 69.3, and it should be per second. And that's the unit of measurement. Yes. You want to get rid of the T half because T half is represented by 0.01 seconds. Yeah. All right, you guys good with that? Yes. Because S is on the bottom of the fraction. Yeah, so it's the same thing as this. If you wrote it like this, 1 over S, that's fine too. But S minus 1 is what that represents. All right. Any other questions? Okay, let us move on to part D. Is it okay if I erase everything? Okay. All right, so let's go to part D. Now in part D, it says the reaction occurs in a 250 milliliter container. How many moles of O3 are in the container after 0.025 seconds? Now, I'm going to give you an opportunity to calculate this on your own while looking at the graph. If you guys remember, this is very similar to the problems we did earlier with this equation, and it's on your equation sheet. The natural log of the final concentration is, minus the natural log of the initial concentration is equal to negative KT. You guys remember using an equation? I think in the workbook we used a variation where this was on the other side, but it's just a rearrangement of that equation. So I'll give you guys maybe about 2 minutes, see if you guys can calculate that out. And then afterwards, if you have some time and if you can solve E, that would be a good way for you guys to see how well you understand this concept. Okay, so I'll give you guys about 2 minutes and then we'll finish up the problem. Okay, so let's plug in our values. And so in this problem, what we want to find is moles of O3 after 2.02 or 0.025 seconds. Okay, so we're basically looking for the final moles. Okay. And so what we're going to have to do is we're going to have to find the final concentration and then convert that into moles afterwards. So make sure you're careful as you're reading the problem. Make sure to give the exact variable that you're being asked to find. Okay, you'll lose points if you only stopped at molarity. Okay, so we want to isolate this variable right here. And so what we want to do is we can just rearrange the equation very simply. Natural log of the final concentration is going to equal negative KT plus natural log of the initial concentration. Okay, if you did it differently than me, if you plugged in your numbers first and then rearranged it, that's totally fine. We'll get the same correct answer or same final answer. So the natural log of the final concentration is going to be equal negative, and then our, our rate constant is going to be 69.3 per second times 0.025 seconds, which is the time that we are interested in, plus the natural log of the initial concentration. And the initial concentration is 1 times 10 to the negative 5 molarity. Okay. Any questions on why we plugged in those numbers for each value? Everybody good with that? Okay, this value right here is basically what you started with in the graph, just the number at the very top, basically. Okay, I'm not going to go through all the math steps, but basically the final concentration of O3, you should get something around 1.77 times 10 to the negative 6 molarity. Everybody got something similar? Yeah. You would probably want to solve out the entire what is it, right side, and then you want to put it both sides to the power of e. Yeah. Yeah.
Right now, it's the power of the answer.
Yes. Sorry, English my second language.
Well, you like overcast that you gotta take something else.
나 영어 잘 못해. 미안해. I'm speaking my first language.
That's cool, actually.
Is it? I don't know. I feel like Korean's a pretty useless language. So you would get your number. So what did you get the number for the left side? 7805. 9.7805. So do you have E on your calculator? Yeah, so you would it probably looks like this, E and then X, right? So you probably press EX and then put it to the and then 9.7805. Yeah. And then that should give you this. Cool. Yeah, as long as you're comfortable using it. Every calculator is a little bit weird. So I recommend using a calculator you're familiar with for the AP test. Okay. So we are not done because this is molarity, right? But we are looking for moles. And so what we're gonna have to do is we're gonna have to set this equal to moles divided by the volume. Now, if you guys take a look at the problem, it tells us it takes place in a 250 milliliter container, and that's going to be equal to a 0.25 liter container. Okay, and so your moles is going to be, oops, I didn't finish that either. Unforgivable. Uh, 4.4 times 10 to the negative 7. And that's going to be your moles of ozone. And that is your final answer for this problem. Something around that. So you remember from the molarity equation that molarity is equal to moles divided by liters, right? So I plugged in this value for molarity. And then I'm looking for moles. We're looking for this value. And then for liters, we have 250 mils. So we just move the decimal 3 times to the left and then plug it in on the bottom. And then we multiply to solve the moles. Okay. Alrighty. Any other questions? You guys excited for your exam? Yep.
So excited.
Good, good, good. I will snuff out that light soon.
It goes test, then Christmas, we don't hear.
Damn, you must love the test. You should give more tests.
I agree.
Okay, so I will leave that up there so you guys can finish copying it down. But let's go over part E, and then that'll be the end of this problem. We can move on to the next one, the next fun problem. Yay. Okay, so let's say that this reaction was conducted again, but this time we used a catalyst. Okay, if you guys remember, catalysts are compounds that lower the activation energy of a reaction. They're just there. They're the wingmen or the wingwomen. Okay, it's the unsung heroes. Okay, will the half-life of this reaction increase, decrease, or not be affected? I want you to write it on your paper, and I want you to explain your answer in terms of activation energy. So you have to talk about activation energy in your explanation. Okay, so this will be good practice. Please try to keep your answers concise, because it's really nice reading your novels on your exams, but there's a lot of exams to grade. And so just know the longer your novels, the longer it will take for me to grade your exams. Okay, so take about maybe 3 minutes to write your answer for part E. First, you want to address the first part of the problem. Make sure you specifically say if it will increase, decrease, or not be affected. And then you want to explain your answer using activation energy. Make sure you answer every part of the question as directly as possible. You don't want the grader to be guessing what your answer is, because they're not going to guess, they're just going to take off points. Okay, so let's start by answering the first part of the question. If we use a catalyst, do you guys think the half-life will increase, decrease, or not be affected? Yes, it will decrease. So make sure you write half-life will decrease. Okay, now we got to talk about this in terms of activation energy. Okay, so I'll give my answer, and you guys, as long as you have something similar, that's totally fine. So we will say catalysts decrease the activation energy, EA. Okay, if the activation energy is lower, more particles will have the energy required to undergo the chemical reaction. Okay, if more particles can undergo the reaction, the rate will increase. Something like that. Let me as long as you have something similar to that, you are good. Make sure you guys talk about activation energy. If you notice, I mentioned activation energy twice. That's pretty good enough. Yes. It's decreasing because the reaction will speed up. Something goes faster, the time decreases, right? Yes. So if you're running faster to the store, it takes you less time to run to the store, right? Same thing. So if the reaction rate increases, the time it takes for it to happen decreases. Yeah.
Cut out the middle part, say activation energy is lower than the rate of increase.
You're gonna want to connect activation energy to the rate of reaction, and that's how you deal with the middle part. If you just got the first two, that's fine, but again, you don't want to keep the reader guessing. You want to make sure you connect. There's a very logical flow with no jumps in logic. Okay, yeah. What do you mean reaction? The rate of the reaction?
Yeah.
How can we slow down the reaction? You could basically do the opposite. You could decrease the temperature. You could decrease the surface area. What other stuff did we say? There was one more. What was that? Oh yeah, you can lower the concentration. You can dilute the solution. Thank you. And then we can't remove, I guess if you want to remove a catalyst, if there's a catalyst, you could do that as well. Thank you. Catalyst will always increase the rate of the reaction, which will always decrease the time. It will always decrease the time. Yes, that's what catalysts do. Yes. Alrighty, you guys good? You guys look so sad. Okay, let's move on to the next one. Okay, let's do which FRQ? 5? Okay, well, 6. Okay, we'll do FRQ 6. This looks beautiful. All right, we're gonna do FRQ 6. All right, we're gonna drop this compound in a insulated container, and it's gonna decompose. Okay, so we got not just the chemical equation, but we got the structures here as well. Okay, so we're going to carry out this experiment to measure the rate of the reaction, and it tells you that it is first order. So that's going to be a good piece of information. This is a first order reaction. Okay, you get a bunch of numbers, and you guys first have to start by calculating the rate constant at 773 Kelvin, which is basically just the temperature that the numbers come from. Okay, so I'm going to give you guys some time to solve out number 1. And then after that, we will go over the answer together. Okay, so for this problem, what we are going to do is first we're going to calculate the rate constant, okay? Now you guys should be able to identify that this is going to be a problem where we need to use that formula again, the natural log, where you have the final concentration minus the initial log, the natural log of the initial concentration, and that is going to be equal to negative KT. Okay. Now, one of the key things you guys want to keep in mind is that our values are given in moles. Okay. So what we want to do is we want to make sure that we divide it by the volume before we put it into this equation. Because if you notice, this equation is concentration. Concentration is measured in molarity. Okay, so the first thing you want to do, and I'm going to erase this in just a second, is we want to calculate using the molarity formula. And if we use the molarity formula, the molarity is 4.7 times 10 to the negative 3 moles divided by 2 liters, and that's going to give us 2.35 times 10 to the negative 3 molarity. Okay, so that is the value that we want to plug in. Okay. So far, so good? Okay, so this is our initial concentration, so we're going to plug it in right there. Now, for our final concentration, it already gives it to us in molarity. So make sure you do not divide it by liters again, because that's the wrong value then. Okay, so we're going to plug it in. So the final concentration is 3.6 times 10 to the negative 4. So we're going to do the natural log of 3.6 times 10 to the negative 4 minus the natural log of what we just calculated, 2.35 times 10 to the negative 3. We're solving for the rate constant, which is K, and then the time it takes is going to be 20 minutes. Okay, so we can write 20 minutes. If you want to convert it to seconds, you can, but you can just give your rate constant in terms of minutes. So that's totally fine. So it looks like you guys are calculating. So I'm gonna give you guys a minute to punch it into your calculator, just so you guys can practice using your calculators. And then in 1 minute, I will put the answer up on the board. Okay, so we got the K value in the previous one, and we'll be using this for the rate law. Now, if you guys remember, this is a first order reaction. So the rate is just gonna be equal to K times the concentration of your compound. And so, hold on. Oh yeah, got it right there. So the concentration of CH3, CH2, and H2. And so all we're going to be looking for is we're going to be calculating for the rate. Now, rate is already isolated. So all we got to do is basically just multiply the two values. So hold up. I'm going to make a little bit of room right here. Okay, so your rate is going to be equal to the K value, which is 0.0938. And then what we're going to do is we're going to use the concentration 2.35 times 10 to the negative 3, okay, which is the initial concentration. And that's going to give us a value of 2.2 times 10 to the negative 4. And that's going to be molarities per minute. Sorry, I didn't write the units of measurement, but it should be minute to the negative 1, molarity, so molarity per minute. Okay. And then the reason why we use, the initial concentration is because you're looking for the initial rate. Okay. So you're going to want to use the initial concentration in conjunction with the initial rate. All right, any questions on that part? Yes, of course. Okay, and then for number 3, you're plotting 1 divided by the concentration of your reactant over time. It's gonna result in a curve. Okay, now we saw in the previous problem with the half-life, remember, with the concentration of your reactant, if you plot it against time, it's going to be a curve. It's a straight line when it's a natural log of the concentration for first order. But for this one, since it is first order, it's going to be a curved line. And so 1 over, and I'll just put R for reactant versus time. That's going to result in a curved graph. Okay. Any questions or y'all chilling? Okay, so we'll take a quick 5-minute break. If you need to go to the restroom, run to the restroom. If you want to just stretch your legs, please go ahead and do that. And then we'll end with one final problem to close out the class, okay? Okay, so for part A, you guys should be able to recognize just based on the stoichiometry. If you guys notice, there are 2 moles of NO and 1 mole of Br2, right? So you should be able to recognize that Br2 is going to appear, what is it? Sorry. NOBr, this compound right here, is going to appear at twice the rate as this one disappears. Okay, so let me just write that somewhere just so we have it as reference. So NOBr is going to appear 2 times the rate as Br2 disappears. Okay, now the reason why we want to compare with NOBr is because that's the one that we have the numbers for. Okay, so after that, it's pretty simple. As long as we can see the appearance rate of NOBr, we just need to divide it by 2, and that's going to give us the rate of disappearance of Br2. Okay, so if you take a look at these values, you're going to see that the appearance rate, we can just pick one of them and then divide it by 2. So we're going to divide, let's divide this value by 2. In experiment 1, it's going to be 1.62 times 10 to the -4 molarity per second. Okay, we're just dividing the rate of appearance for NOBr. We're dividing it by 2 because Br2 disappears at half the rate. Okay. And it's because we're looking for experiment 1. Yes. So you can describe it as NOBr appears at twice the rate, or Br2 disappears at half the rate of the appearance. Okay. Okay, so now we want to figure out the order for each reactant. So we got to compare between some different experiments. So if you compare 1 and 2, NO is held constant. And if you take a look at Br2, how does the value change? Yeah, times 2. Okay, and how does that affect the rate? It doubles. So if doubling the concentration doubles the rate, what does that tell us about the order of Br2? Yeah, first order, exactly. We will get there. Okay, so next we want to take a look at NO. Now NO is a little bit trickier because if you guys notice, there's no constant Br2. So we gotta do a little bit of math in order to figure that out, okay? So we want to pick 2 experiments where the NO rate is not constant, and that way we can compare the values. So the easiest way to take a look at this is probably to take a look at this one right here. Okay, 1 and 3. So if we take a look at 1 and 3, how does the the concentration doubles? Okay, and then if we take a look here, what happens to the concentration of Br2? Yeah, divided by 2. So it's the opposite. Okay, so we want to take both those things into consideration as we compare the rate. Now, if you take a look at the rate, it goes from 3.24 to 6.42. Okay, so what we want to do is we just want to write a quick equation in order to compare these 2 values. So I'm going to show you guys how to write that equation right here. Let me make some more space. So we know Br2 is first order, so let me erase this. So let's pull it up. Okay, so this is how you want to compare these two equations. Okay, so the rate for experiment 1, okay, we're gonna compare it with a ratio, okay, over the rate of 3. Okay. And then on the top of the right side of the fraction, we're just gonna equal it to the rate of 1. Okay, we know the rate of 1 is K, and then it's the concentration of NO, concentration of Br2, okay, which we know is 1. Okay, and then K of NO times the concentration of Br2, which is also 1. And then what we are looking for is basically the rate order or the order of NO. Okay. Does that make sense? Okay. Okay, so what we want to do is we're basically looking for the order of NO. Now we can get rid of some variables right away. We can cancel out K on the top, K on the bottom. We can get rid of the BR2s because that's going to be the exact same value. Okay. Oh, sorry, we can't cancel that. My bad. The concentrations are different. Sorry. We can cancel out the K's. Now for BR2, we're going to plug in the numbers that we have right here. Sorry about that, guys. Okay, so for experiment 1, we're going to put in the concentration of BR2, which is 0.012. And then for the concentration of BR2 for experiment 3, it's going to be 0.006. What is he doing? What in the world? Okay, and then we're going to fill in the concentrations for NO for each of the reactions. So we're going to put 0.16 on the top and 0.032 on the bottom. Yeah, so here it's just algebra. All we're doing is filling in the values from the table. So the rate for 1 is 3.24 times 10 to the negative 4. The rate for 3 is going to be 6.42 times 10 to the negative 4. Okay. We all good? Okay, so since we are running out of time, I'm just going to give you the final answer, and you guys can try punching this into your calculators as you guys are studying. But for the rate order of NO, you're going to get a value of the rate of NO is 2. So you're gonna be able to get M is equal to 2. Okay. So your rate law is going to be K, the concentration of NO squared, and the concentration of Br2 to the power of 1. That's going to be your rate law, okay? NO is second order, Br2 is first order. Yeah. Yeah, so if you can identify that pattern, that works too. You know, this is about as complicated as the rate law is going to be. Yeah. Alrighty, guys. So you guys can pack up.